Okay, thank you for invitation. In this talk, I'll talk about on the dynamical core of Aeolus 2, a moist convective thermal rotating shallow water model with intermediate complexity. In fact, this study, let me make the slides. Okay. Can you see the slides now, right?
Yes.
And okay, so this approach, in fact, is about how we can include the effects of moist convection in a thermal rotating shallow water system. Before going toward the details, so at first I'd like to show this slide. This slide shows that, in fact, where we are. In this slide, you see a plethora of related geophysical fluid dynamic approximations. You see at the upper level, we have three-dimensional Euler equations for the stratified rotating incompressible fluid. And then we have three-dimensional Euler Bouziness equations for stratified rotating incompressible fluids. Then on the left hand side of that, we have primitive equations with stratifications. Once we have vertical integration from primitive equations, we have shallow water systems. But the question that how we include, in fact, the temperature in the shallow water system is the question of also our preliminary studies, that in fact we switch from shallow water, classical shallow water system to thermal shallow water system. So it means that we have also somehow the temperature or potential temperature or buoyancy fields as an independent variable or independent character. Also, it's not independent physically, but we can have, in fact, we can capture the evolution of the buoyancy or temperature or potential temperature field. And so it's very interesting because in the classical view, once we are talking about shallow water system, we expect we have a constant density, constant buoyancy at each layer. But here the temperature, the density and potential temperature are not constant for each layer, are not homogeneous. So we deal with something that it's very interesting, and on the other hand, it's complicated because what's going on for conservation laws, So we are here in the thermal rotating shallow water system. This paper, in fact, shows the derivation of in this system, that where we start, what are our starting point, and how we include the moist convection and latent heat release, vaporization, and so on in the system. And also this paper includes the derivation of the system. An application of the system for some extreme events like heat waves, or vessel jets. In this talk, I'll show you also an application of this system for Madden-Julian oscillation and our recently developed theory for mechanism of the Madden-Julian oscillation, which is based on moist convection. And it's one advantage of the shallow water system is that it's very, very applicable for theory building, for people who are working in the theoretical atmospheric dynamics. It's very, very handy because shallow water systems are robust, are reliable. We deal with layers, not levels. And it's amazing, and we can capture barotropic and baroclinic instability very in a clear manner, in fact. So let's going on toward the reduction of the atmospheric primitive equations in the two-layer system. In fact, in two-layer, which is a simplified version of the multi-layer, in fact. As usual, you have momentum equations, mass equations. But if you look at equations, in fact, we see that pressure in this system, in fact, is not a gradient of scalar. It's a gradient of a combination of H and B. B in these equations is the buoyancy, and 1 is for the lower layer and 2 is for the upper layer. And so you see that the momentum equations, we have on the right-hand side some drag forces due to condensation. What is new, in fact, with respect to our previous systems, because it's over a decade that we are working on the inclusion of moist convection in shallow water system. At the beginning, we were thinking about how we can include condensation in the shallow water system. So condensation in our previous works looks like a sink of mass. So if you look to the, for example, H1, which is in fact, the mass equation in the lower layer, or if you consider in the simplified case just a simple one-layer shallow water system, C, or condensation, acts as a minus, you have a minus coefficient. So it means that it acts as a sink of mass. It means that once there's a latent heat release, in the classical version that we developed, in fact, we lose the mass from that layer. So we have a drainage or a sink of mass. And during the time, once we have a sinking of the mass for a long term, we lose, in fact, all mass if there's always a moist convection. So in the revised version, we added this D. D, in fact, is a downdraft. So it means that once we have a moist convection, C acts as a sink or updraft, because after latent heat release, it loses its density, becomes lower and goes in the upper layer. And so we need another downdraft to compensate these losses of mass. So D in this system is a downdraft on the right-hand side of mass equation. And the total D is equal to C, in fact. I mean, if you integrate over the space, the total downward is equal to, in fact, total upward. So it's the role of C and D. But F, in fact, in this system is any external or other forcing, because we don't have in the real atmosphere just condensation and downdraft and updraft. We have radiative transfer, we have a bunch of other forcings, greenhouse gases effects, and so on. So everything, any other forces can be included in this capital F1 or F2 for lower or upper layer, and gamma is a coefficient that can be adjusted and also can be dependent or different even for each layer, but for simplicity here are the same for both layers. And if you go down, you see that we have also buoyancy field, but in fact on the right hand side of buoyancy you see the signs of the C is changed, because once we have latent heat release, it increases the potential or temperature in that layer, and it increases also the buoyancy. And once we have also surface evaporation, as you see, as E, with the coefficient of mu, which is in fact just to adjust the conservation of the buoyancy fields. Also, you see that acts as a cooling. So, but here we don't have updraft or downdraft. Here is in fact just we have increase or variation in the buoyancy field due to latent heat release. And Q1 and Q2 are in fact humidity. And here we have also tracer fields of humidity, which is also a function of all this upward, downward condensation, sea surface evaporation, and so on. So in this system, we have adiabatic convective equations and diabatic non-convective effects, in fact, in the system. And this scheme shows, in fact, the big picture of the system. As you see, we are in a system, in the atmosphere, in contrast to the ocean, in the ocean system, we have rigid bottom, but in the atmospheric system, we have rigid lid. Because if you want to derive the equations and finally you write your equation with respect to H, not with respect to surface levels like Z1, Z2, Z3, and so on, you will need to have a rigid lid. And also in this system, you see that we have sea surface evaporation with our new introduced scheme, which is a function of buoyancy and wind, and also water vapor and condensation, which is in fact once humidity reaches to a threshold value in a convergent zone, it will be condensate, and it's approach that works for larger scale atmospheric structure. And we have moist convection and also precipitable water, which in this simplified system can be interpreted as clouds. And we have also radiative transfer, insolation. If we want to switch to or go toward the intermediate complexity, we have also radiative transfer, long wave, short wave effects in two-layer system. It works well for the lower and upper troposphere in the atmosphere. And in fact, the question that what's going on for the conservation laws, one advantage of the shallow water system, which is robust with respect to Hamiltonian structure, and it's one of the advantages because we are not in a black box. So as you know, we can write down, in fact, shallow water system in a Hamiltonian structure. In fact, Hamiltonian, the question is that what's going on for the Hamiltonian structure? But just to remind you that if a system is Hamiltonian, then the evolution equations governing the field variables like phi A can be expressed utilizing the generalized Hamiltonian structure as shown here. You know, the differential equation with respect to time can be written down as in fact, the multiplication of J, which is in fact the Poisson tensor, and also partial differential of Hamiltonian with respect to that state variables. So if we go toward this system, two-layer system, in fact, Hamiltonian structure, which is also can be interpreted as total energy, because once we are in adiabatic system, Hamiltonian structure or total energy is conserved. So the question that what's going on when we switch to the moist convection, because once we switch to the moist convection, the system is not adiabatic, the system is diabatic or non-adiabatic, and also total mass or total energy is not conserved anymore. But as I showed in the derived equations, with that trick, we can respect still the total conservation of mass and buoyancy once we adjust, in fact, the downdraft and updraft. But let me remind you that once we have the updraft where the condensation occurs, we have a downdraft in the vicinity of the updraft. So the downdraft in our system is not uniform. Wherever there's a condensation, close to this condensed region, we have more downdraft, but once we go far away, it goes down. So it's not uniform like the classical parametrization. So as you see, we have a Hamiltonian structure for two layer. H1, H2 are thickness, and V is velocity, and B1 and B2 are buoyancy field, which is a function of potential temperature in two-layer system. And in fact, the potential vorticity also can be written down like this, is a function of 1 over H, Jacobian of H and B. So what's going on for potential vorticity once we switch to the moist convection in this system? If we derive the potential vorticity and compare it with what we had in the dry case, you see that we have external terms, other terms on the right-hand side, as you see here, minus 1 over HB1 Q1 alpha I. In fact, alpha is in fact a function of condensation and the downdraft, or cooling and warming, or updraft and downdraft, and so on. So in fact, each of them in fact, for each layer have different effects, and so we can write down, in fact, the potential vorticity equation in this system, which we call it most convective thermal rotating shallow water system, or MCTRSW. And one criteria once we are going toward the shallow water system is the hyperbolicity loss. As you know, once we switch to the moist convection, we should care about Kelvin-Helmholtz instability.
Hello. Hi, Masoud. Can you hear?
Yeah.
Just a question in between. So can you go back to the starting of the equations you wrote down? Can you explain how you introduce buoyancy in those two layers? Because that seems to be coming up again in the Hamiltonian formalism.
Yeah.
You're still going with constant density in each layer. How is that you're introducing a buoyancy then?
Yeah, in fact, in the Hamiltonian, here it's in fact showing the potential vorticity, but for buoyancy, as I showed, it's here. You see, 2.11 E and F, B1 and B2.
Right, so is density still constant in each layer?
No. Density, in fact, here is translated to buoyancy, in fact, in the atmospheric layer. In fact, you see buoyancy is G theta over a constant theta.
Right, and so theta constant in each layer?
No, it's varying. In fact, B1, you see, on the right-hand side is not 0. You see, on the right-hand side of the B1, you see B1 on the right-hand side, it be affected by condensation and evaporation, or downdraft, cooling and warming. So in the buoyancy, in fact, once we have condensation due to latent heat release, buoyancy in the lower layer increases and the upper layer decreases. So also here, I should just say that here we consider condensation, if we consider condensation just in the lower troposphere mostly. So in fact, the buoyancy is not constant for each layer. It varies. It's a spatiotemporal variable, in fact.
Okay, so now do you still have conservation of energy? The standard.
Yes, still we have conservation, but this conservation is not by, in fact, physics, but it's by, in fact, parametrization. Because parametrization of this C and D are in a way that if you integrate over the space, and then it's conserved, because total D is equal to, at each time step, total D is equal to total C, and here also total mu E is equal to total C. So if you neglect this other forcing F1, F2, still we have a conserved system. It's in fact the parametrization that applied for this Moist-Convective TR established system. Okay. By the way, it's a bit challenging, and maybe understanding is for some guys is a bit complicated, but derivations are in our paper, so the people who are interested can refer to them. Okay, so hyperbolicity laws, in fact, V1 and V2, in fact, should obey, in fact, this equation. In fact, this one is hyperbolicity criterion that we can write down in a two-layer system. And regarding the model itself, which we called it Aeolus 2, in fact, the solver is Daedalus, and Daedalus, as you know, is a pseudo-spectral spherical harmonics. In fact, it uses spectral spherical harmonics. We have once you are in this system, so if we have a transition from grid space to coefficient space, and then again from coefficient space to grid space. So we have transforms, and also it works parallel in this system, and we write down equations in a way that we have this matrix form or flux form of the equations. And then the system on the sphere, you can choose that which type of collocation grids you want to use, for example, Fourier, Chebyshev, Lorentz, Hermite, and so on. And one advantage is that the system, this Daedalus solves fronts very well. So it captures the shocks, and there are some numerical advantages, in fact, with this spherical harmonics over the sphere. One other advantage is that we are not using the classical coordinates here. We are using a spin-weighted spherical harmonics. So it means that each each basic vector is a combination of E theta and E phi. So one advantage is that once we are switching to a spin-weighted spherical harmonics or coordinates, gradients are regular, because otherwise you have singularities over the poles for a sphere. But here we get rid of the singularities by switching to this spin-weighted set of basis vectors. And as you see here, regulars are gradients are regular everywhere. So its gradients can be converted to just multiplications of other variables. So here is one advantage of spherical harmonics that Aeolus is using the solver, and this scheme shows that once we want to switch to the intermediate complexity or hierarchy levels of complexity, because one problem for scientists is that or either they are using the very idealized case or complex system, which is like a black box. And if we want to know what's going on between them, so we need a hierarchy level of complexity. We can start from very, very idealized case and make the system a step-by-step complex by adding, for example, bottom topography, moist convection, radiative transfer, also transfer in this system is rapid radiative transfer model, or RTM, which guys, that is the second best radiative transfer after line by line, which is very expensive numerically. But this one is fast and can, in fact, capture most greenhouse gases effect. And also, we have a type of water cycle in this system. And so this set of scheme, in fact, shows that we can start from idealized case to intermediate complexity, and other physics, if you know the physics, can be included in the equations too straightforward. So it's not complicated. And one application of the thermal rotating shallow water system that we applied it a few years ago, it's about how can we capture the effects of the moist convection on the larger scale structures like Madden-Julian oscillation system, which is the, in fact, if I show, in fact, also here, if we have a set of studies, once is this one, which is with thermal shallow water, but before that, even with just simplified moist convection in shallow water system, we showed that it might be also a geostrophic adjustment as a source of, in fact, a dynamical backbone structure of the MJO. And in fact, in this structure, let's first start to explanation. What is the MJO? Most of you, maybe you know already. Madden-Julian oscillation is the dominant, slowly eastward propagating mode of intraseasonal planetary scale variability in the tropical atmosphere. So any theory should explain, in fact, the backbone structure. At first, it should show the eastward propagation. Secondly, it should show that it's a slowly eastward propagation. Third, it should show that it is in fact, the structure, vertical structure is comparable with MGO-like structure. And also it should show that it is a type of intra-seasonal variability, and it is not forever. It works just for a specific time span. And so any theory should capture at least main features of the MJO, which is the larger scale pattern, deep convective structure, a slowly moving eastward propagation, and it should show that it will die out over the Pacific Ocean. As you see, it will start over the Indian Ocean. It's the biggest, most convective atmospheric structure in the world, and even it affects the polar regions, ice melting. So it's very, very important one. And it starts initiates over the Indian Ocean, goes eastward, and then passes maritime continent, and over the Pacific Ocean, it dies out, at least in the lower troposphere. In some observations in the upper troposphere, still some structure circumnavigates all around the world and starts again the MGO initiation. So, but what we offered, in fact, is that MGO structure is a self-sustained and self-propelled manner due to moist convection, due to nonlinear adjustment of the large-scale positive buoyancy anomaly or depressed anomaly or combination of them, as soon as this anomaly reaches a critical threshold in the presence of moist convection at the equator. So moist convection as initiation of this structure is one of the necessary conditions, but once generated, this structure can go eastward in the idealized manner, but in real world, it will die out, and I show you why. And in fact, here we have a interaction of baroclinic Kelvin wave, and after circumnavigation of this upper layer structure, which is also dry, once it hits to a new buoyancy anomaly over the Indian Ocean, it can trigger a new cycle of MGO. So this theory, in fact, also this explanation also shows the regenesis or recurrent structure of this structure, and also we find out that there might be a quasi-equatorial modon in this system. But what is the modon? Equatorial modon is in fact exact formal preserving eastward uniformity translating horizontally localized nonlinear solution in the inviscid quasi-geostrophic equations. Also, this is very precise definition, but each of these terms in fact has its own meaning. So just in the simple words is that, as you see, this is a pressure field of equatorial modon, 0 is equator. So this equatorial modon is a coherent structure that goes eastward in the idealized shallow water system. Once you initialize the system with equatorial modon, it goes eastward forever in the idealized system without moist convection. And if you initialize the system with just velocity field that comes out from in the Charney regime, it goes eastward, and this pressure field will be created by the system. So it's amazing because, in fact, if you initialize the system with just velocity field, no pressure, and initialize this asymptotic solution, how we derive this asymptotic solution, you can refer to the papers, but it is the structure of the velocity. In fact, we call it this extreme lines and velocity field of asymptotic modon with and without co-moving frame. If you initialize, for example, left-hand side in a shallow water system, you see that pressure field will be created automatically. It's a self-propelling in a self-propelled manner, and then it goes eastward in a coherent manner. As you see here, you know, the asymptotic modon at time zero is a pressure field, but at time 0, there's no pressure. We have just velocity field. But as you see, as time goes on, also these times are non-dimensional, in fact, so it's you should convert it to days or something. So you see that after emission of some gravity wave due to adjustment, we have in fact this adjusted equatorial modon, and this equatorial modon in fact is a coherent structure. As you see, asymptotic solution has in the Charney regime, we have some in fact, stream functions there's analytic solution for asymptotic modon, as you see, for internal and external, in fact, psi here for as string functions, and then under Charney regime. Also, derivation is a bit maybe complicated. We can pass this part, but it's important you know that we are in the leading order. Once we are talking about asymptotic solution, it means that we rewrite equations in the leading order. As you see, V naught is the leading order or the dominant velocity in this system. And the Charney regime says us that on the equator, in fact, the vorticity or potential vorticity are dominant, are very important material for us. And so a steady modon that we introduced in 2019, in fact, as exact solution, and we called it also a dipolar system. Because it's a dipole. It has two poles, so it's a dipolar system. And once you derive the equations, we can have also pressure distribution as a function of stream functions, as you see here, as a Hessian operator, and so on. So, but what's going on? What is the relation between the equatorial modon? Is that once we have in the two-layer system, but the equatorial modon is for one-layer barotropic system, but in the real MJO, we deal with two-layer at least. And so it's there's a vertical structure, changes the sign, the vorticity changes the sign. So if we initiate, in fact, the moist convection in the lower troposphere, amazingly, we see that what goes on the structure is very, very similar to what we saw in the equatorial modon. So we called it quasi-barotropic equatorial modon. In fact, it's not exactly the equatorial modon, because equatorial modon is the coherent structure and goes eastward forever. But once it's the quasi-equatorial modon or quasi-barotropic or somehow baroclinic, in fact, equatorial modon, in fact, this is not coherent, and so it, as you see in this structure, we have two structures. In the upper panel, we have a dry case. In the lower, there's a moist convective case. As you see on the right-hand side of this panel, there's a baroclinic Kelvin wave that detaches from the left part, which is the dipolar structure. So MJO in this definition, in this explanation, is a hybrid structure. It's linking of two structures. One is the dipolar system, which is also observed in the observational studies. We see this dipolar, a signature of these dipolar vorticities. And on the head, we have a baroclinic Kelvin wave, but it's not exactly baroclinic, because baroclinic speed is about 12 meters per second, but this structure, this hybrid structure, is between 5 to 8 meters per second. So explanation is that once we switch to the moist convection, this links, in fact, this attachment occurs, and this baroclinic and this equatorial modon will be linked, and so the total velocity is between 5 to 6. So it will decrease, in fact, the eastward propagation. But once the detachment occurs, because the essence of the baroclinic structure is not 5 meters per second, and the essence of the barotropic equatorial modon is very, very slow. So once they detach, and this detachment explains that why the MJO-like structure will die out over the Pacific Ocean. As you see, also, we can recreate this MJO structure in three ways, in fact, just to support this idea. One is we have a buoyancy anomaly, as you see in these panels are, in fact, evolution of buoyancy anomaly, which is potential temperature anomaly, or in a simple words, high SST anomaly, temperature variation. that affects also once it reaches to the threshold value, we have a initiation of moist convection. And once we initiate, we see this quadrupole structure. In the equatorial model, we have dipolar system, but in the MGO structure, we have quadrupole. But the left part, which is the dipolar system, is the signature is much stronger than the right side. As you see, the signature of the vorticity is much higher than the other part. And once we developed this system, we went to the dynamical system or dynamics of excitable systems. We called it equatorial excited dipolar systems. And the advantage is that here, this scheme shows the excited dipolar vorticity. Once we have a moist convection in the equatorial region, the system will be excited. And after excitation, we have a dipolar system, which is two, in fact, poles of the high vorticity that you see in blue circles. And then this dipolar system will generate the secondary anticyclonic circulation in the lower layer. And as you see, whatever is in the lower layer, the opposite sign is in the upper layer. So you can have, in fact, in the lower layer, if you have the sign of anticyclonic and this circulation on the right-hand side of this dipolar system, on the upper side, outer troposphere, you have a cyclonic circulation, which is the signature of vertical structure of the MGO-like structure too. And so just to wrap it up, it shows that buoyancy goes eastward. And so you see that here we have eastward propagation and corresponding precipitation of the buoyancy field in the Hofmüller diagram that goes eastward. And also you see that this hybrid structure due to high buoyancy anomaly and deviation of this and evolution of this buoyancy anomaly and corresponding speed of them, you see that it's a slow varying. And the other thing is that the recurrent generation of this MGO-like structure because if after dying out in the upper layer, still this baroclinic Kelvin wave goes on even in a dry system and circumnavigates all around the world. Once it reaches to a high temperature anomaly, as you see in the left panel, it's a recurrent generation. Also, the recurrent generation you see is not as clean as the first generation. And then we can have a recurrent generation of the system automatically again, and we see this eastward propagating. At first, also the speed at all phases of the generation are not equal. At the beginning, it's a bit faster. Once it dies out, in fact, Kelvin waves becomes faster, but the dipolar becomes slower, as I explained, and so it's a bit complex. Thank you for your attention. I stop here and I'm open for your questions.
Thank you, Masoud. So do we have questions?
Am I audible? Masoud, so many of those papers you cited, right, use shallow water equation. Now, shallow water equations have the shock formation tendency. Waves break and form shocks. And at least some of those papers with moisture, you see that the moisture dynamics are very coupled with the shock dynamics. Right now, in realistic, if you look at more realistic model like elastic or Businesque, the shock form, you don't see waves breaking and forming shocks like in shallow water. So are many of these results affected by the shock formation dynamics?
Yeah. In fact, once we are talking about the shocks, we should distinguish, I think, between the physics and also numerical shocks due to instability of the numerical systems. in fact. For example, what I showed here in the front resolving of the system, you see that, in fact, in the numerical and also in reality, once we initialize the shallow water system, for example, with Kelvin waves, at the beginning, it follows the analytical solution, but then it becomes compacted and recreates a type of front. So any front, in fact, once you switch to the moist convection, the location of the condensation, where the condensation exists, and the location that where the condensation does not exist, automatically we have a shock. So the numerical model should capture, in fact, this shock, and there are some systems so numerically that can capture the shocks, and because finally we need a stable system. So for example, some finite volume schemes with Shinjin and Alexander Kurganov, we developed a type of numerical scheme which is so-called path conservative central upwind scheme, which is a type of finite volume scheme that respects to this path conservative system, and this path conservation can respect and also solve somehow this problem of shocks. So shocks exist physically, and also, but some of them, if the numerical scheme could not solve it it will explode. So in fact, yeah, you are right. So there's a very delicate, in fact, needs a delicate attention between these different shocks that exist in the shallow water system. Yes.
Hi, Masoud. Thank you so much for that talk. As I understand it, Aeolus 2.0 is primarily an atmospheric model, but I'm just curious. You mentioned that it could be used to simulate extreme heat waves. I'm wondering if it can be used to simulate marine heat waves like the blob over the Pacific, or if it has been done before, or if it hasn't, then can it be done?
Yes, yes. In fact, one advantage of the thermal rotating shallow water system is that now we have a buoyancy equation, as I showed you in the set of equations. So we can capture, in fact, the effects of buoyancy field. But once we are talking about the heat waves or shocks, in fact, is that if you initialize, for example, other systems like GCMs, maybe it cannot capture in a simple manner. As you see here, B1 and B2 here are very robust, in fact. So even if your system is conserved, which is the case here, you can have also as long as you wish, for example, the high potential temperature anomaly, and the system can capture its evolution. Also, we already did it for some localized buoyancy anomaly, which is, for example, surface temperature anomaly for the mid-latitude and for also subtropical regions. But yes, it's straightforward. You can define any type of initialized buoyancy anomaly and let the system go on, and it can capture as independent as a diagnostic, in fact, as a diagnostic. So you have B1 and B2. For example, once we have B1 buoyancy anomaly in the lower troposphere, automatically in the upper we have buoyancy anomaly, negative anomaly. So it can capture, for example, cyclonic and anticyclonic simulation once you have the local buoyancy anomaly in everywhere, in tropical region or mid-latitude or polar region or whatever. So heat, in fact, in this context is a buoyancy field, in fact. Yes. Thank you for your nice question.
Sorry, I'll try to make it quick. I just have one more question. So the model is used to study the atmosphere or the ocean in isolation. I was wondering if there's any advantage to adding a feedback, an ocean atmosphere feedback into the equations itself, or if the essence of the model is to study the fluid in isolation.
Yes, in fact, regarding the feedbacks, there in the standalone version, we have sea surface evaporation, but this feedback of what's going on, for example, for land or other components, it needs switching to a coupled version. Also, in the coupled version, which is other air system model, in fact, it dialogues with other components like land, ocean, ice, and so we can have a full interaction of these two together, because if it's not coupled, we cannot. Also, we can include also land in this system, but it's something maybe does not make sense because the land model already exists. But it needs to switching from a standalone version to the coupled version. Also, we already have a coupled version, so-called POEM, with Potsdam Air System Model, which is under development, and it can be one of the solutions, but it can be coupled to any other ocean or land model too. For example, to capture evapotranspiration and other effects of the leaf area index, vegetation, and so on. Thank you.
Thank you.
I have a question regarding the convective parameterization that you have used for your moisture equation. So I'm assuming you've used the Betz-Miller parameterization, is that correct?
It's a modified Betz-Miller, yes. It's a bit modified because, in fact, the surface evaporation here, in fact, is different. But the Betz-Miller equation, yes, here it's proportional, because if in a simplified equations of humidity, you see then the leading order, it's proportional to minus divergence of velocity. So if wherever there's a convergence,
I was curious about that, because you would have to use the relaxation time limit going to 0, and that seems a bit unrealistic, because typically you would see the relaxation time in the order of hours. Is that so? How exactly is this? So this is also bringing, like the sort of nonlinear phenomena because of the Heaviside function you're using.
Yes,
so
yes.
So how exactly are you addressing this issue, or is this an issue with the model you're using?
Yes, in fact, relaxation time is not 0. Yeah, and it should not be 0, because also fast relaxation, it does not mean that it is 0. In the equatorial region for deep convection, some papers say it's about, for example, about hours or half hours or 1 hour or something. So, and numerically, there's at each time a step we cannot have very fast. So, in fact, in our numerical scheme, for example, it's about 50 to 100 time a step. It takes time. There's relaxation time depending on what's your parameterization. So, relaxation time in this context is fast, but it's not 0. But the part that it showed that 1 tau goes toward 0 is some mathematical, in fact, understanding of the equations. Once we simplify in the leading order and go toward the 0 relaxation time, we see that condensation in the leading order is equal to minus divergence of velocity multiplied by initial Q or humidity. So it is the, in fact, maybe it's misunderstanding and for my explanation. So there's a distinguish between the, in fact, zero in the mathematically for driving the leading order, but what's going on in the real atmosphere and in the model itself. And by the way, in some papers shown that the relaxation time cannot be less than 10 time steps, at least numerically or mathematically, because otherwise the model will collapse. So it's the definition, I think, I could answer.
Okay. I think we do not have any more questions, so let's thank Masoud again. Thank you, Masoud, for starting your day earlier than usual for this talk. So
Thank you for the invitation.